Hello everyone, welcome to the last regular talk of this term. Just before the talk starts, let me say a few organizational things. Even though there will be no more talks on Thursdays until the end of the term, there will be a pub quiz and social event this Sunday and a symposium on Sunday next week. So we hope to see you there. And now let's get back to our today's talk. It will be about an hour long and there will be a Q&A session. Both will be live streamed on YouTube and also recorded. To ask questions, please write them into the YouTube chat or you can join the Zoom call for the Q&A. The link will be posted into the YouTube chat just before the Q&A. Please join the call with your full name and mute the YouTube live stream beforehand. And now let me introduce our today's speaker, Professor Harry Anderson. Professor Harry Anderson works in the Department of Chemistry, University of Oxford. He's well known for his contributions in the synthesis of supramolecular systems, Porphyrin nanorings and nanowires, and exploration of the extraordinary physical properties of large pi-conjugated systems. In today's talk, Professor Anderson will be speaking about the molecular nanostructures and their interesting properties. Please welcome Professor Anderson. Professor Anderson, the stage is yours.
Thank you. Well, thank you very much for inviting me. It's a shame I can't come to Cambridge and meet you personally, but I'm pleased to be able to give you this talk, and I hope we can have a good discussion afterwards. So I'm pleased with the chance to tell you about some of the things my group has been doing on the synthesis of molecular nanostructures. Maybe I should share the screen. That's working, isn't it? Yeah. The most exciting thing to me about chemistry is that you can make molecules that have never existed before and investigate their properties. And it's easy to be overwhelmed by the diversity of molecules that we could synthesize. My approach is to focus on the synthesis of molecules that I think will have the most remarkable and unusual properties so that we can test whether they really behave as we expect. And today I'm going to tell you about some molecules that have very unusual electronic properties. But first, I thought I should remind you about Moore's law. So Moore's law says that the number of transistors in an integrated circuit, like the integrated circuits that we have in our computers and mobile phones, doubles about every 2 years. And the amazing thing is that Gordon Moore put forward this law in 1965, very early in the days of integrated circuits. And most people said, and most people have been saying since then, that this law might apply for a little while, but it will soon cease to apply, that the exponential increase in the number of transistors surely won't continue very long. But well, so far it has pretty much continued. If you plot the log of the transistor count against date, you get a fairly straight line right up to the current day. And that means that at the moment we're all using devices that have integrated circuits with about 10 to the 10 transistors integrated onto them. So that's more than the number of base pairs in the human genome. And it's almost as many as the number of neurons in the human brain. So there's a huge number of transistors integrated into these integrated circuits. And of course, it's possible to do that because the transistors are very small. And this graph shows how the critical dimensions of transistors have decreased exponentially over the last 50 years. Chemists often get very excited when they see this sort of plot because it points towards the size of transistors reaching the molecular domain, and so molecular chemistry being the solution to making new electronic devices. I think that this plot can be a bit misleading because although in the 1990s and 1980s, the way that Moore's law was achieved was by reducing the size of the transistors so you could fit more in a chip. More recently, the size of the transistor has actually stayed more or less constant, and it's only a few critical dimensions, like the gate length, which have reduced down to about 10 nanometers. And the way in which people have got more transistors onto a chip has not been so much to make the transistor smaller as just to increase the size of the chip. And of course, there are huge unanswered questions about how you might ever make a molecular scale electronic device. But still, I think this shift in integrated circuits towards molecular dimensions makes it important and interesting to ask how single molecules behave when they conduct electricity. And it's also an important question for making other sorts of devices like photovoltaic cells. So single molecule conductance means the conductance of a molecule when it's connected directly to metal electrodes. And 20 years ago or so, it wasn't possible to wire up a molecule reliably and measure its conductance. But now there are quite a lot of methods which can, with some reproducibility and accuracy, measure single molecule conductance. So I thought I'd talk about just one of those methods, which is scanning tunneling microscopy. So how this works is that you have a gold surface and a gold STM tip, and you bring the tip down onto the surface and actually just crash it into the surface so they weld together. And then you pull the tip away from the surface, and you tend to string out some gold atoms, and then it breaks. And if you apply a potential between the tip and the surface, you can plot the conductance, or in this case, the log of the conductance, against the distance as that tip moves away from the surface. And what you find is that you get an abrupt break, of course, where the gold breaks, and then the conductance decreases exponentially. That's just because it's a tunneling current. So on a log plot, you get a straight line. So that's what you see when you have no molecule present. But if you do the experiment with a few molecules present, then occasionally they get trapped in that gap, particularly if they have N groups that tend to bind to the gold. So they get caught in the gap between the tip and the surface. And when that happens, you get a trace shown like this red trace in the conductance against displacement with a plateau. And that plateau is when the electricity is passing through the molecule, the currents passing through the molecule. And the plateau breaks when the molecule disconnects. So from that plateau, you can get an estimate of the molecular length, the length at which it breaks off, and also the single molecule conductance. Now, every time you do this experiment, you get a slightly different trace because the molecule can be in a slightly different arrangement. So you have to do it hundreds or even thousands of times to get a statistically significant result. And that looks like a histogram like this, where you can see over many traces, you get a probability density here representing the plateau. And from that, you can measure the conductance of a single molecule quite accurately. So one of the questions that is interesting to ask when you can measure the conductance of a molecule is, how does that conductance change as you make the molecule longer? How does it change with the distance, the length of the molecule? And the simplest way to understand this is to see the molecule as a tunneling barrier. So the electrons don't have enough energy to populate states on the molecule, but there's a certain probability that they'll tunnel through it. And normally you'd expect tunneling to fall off exponentially with distance. So the conductance G falls off exponentially with the distance D, as quantified by this attenuation factor beta. So you can measure beta for different sorts of molecules or different media, and you find that you get a larger value for a saturated hydrocarbon than you do for a conjugated pi system. So the smaller beta, that means the less attenuation, the easier it is to transfer charge over a longer distance. And the reason why pi conjugated molecules allow longer range tunneling is that they have a smaller HOMO-LUMO gap. So this energy gap, delta E, is important in determining the attenuation factor beta. So for the simplest possible model, beta depends on the square root of E. So if we're thinking about how well molecules will conduct electricity, we need to think about the HOMO-LUMO gap or pi to pi star gap of the molecule, and perhaps how that will change with length. So if I can remind you just about the idea of pi conjugation, if you have a very simple pi conjugated or a simple unsaturated molecule like ethene, you just have a pi and a pi star level. And if you join ethene units together, you get butadiene which is conjugated. And that means that there's a destabilizing interaction for the HOMO and a stabilizing interaction for the LUMO, and the HOMO-LUMO gap gets smaller, the pi to pi star gap gets smaller. And as you carry on joining units together, you reduce that gap, the pi to pi star gap gets smaller the longer your conjugated pi system. And you might imagine you'd eventually arrive at an infinite polymer where you just had one band derived from all these discrete molecular energy levels, which would be half full. And that would mean that the material would be a metallic conductor. So if you have a non-zero density of states at the Fermi level, the material is a metallic conductor. And that's what you'd expect if you have this sort of infinite polymer with no alternation in the bond length. If all the bond lengths along the chain were equal, you get this single half-full band, which would be metallic. But in fact, that's not a very good description for what happens. There's a distortion, a bit like a Jahn-Teller distortion, known as a Piles distortion, that lowers the energy of the system by lowering its symmetry, so that you get shorter double bonds and longer single bonds along the backbone, and the band splits into a full pi band and an empty pi star band separated by a small band gap. And I just thought I'd show you some experimental data that illustrates how this happens. So if you look at the absorption maxima for a series of polyenes, so these are just hydrocarbons with alternating double and single bonds, plotted as a function of the length or the number of carbon atoms. So this is the lambda max, the absorption wavelength. And you can see it shifts towards longer wavelength, smaller excitation energy as the chain becomes longer. Now, an easier way of seeing those data is to plot 1 over the absorption wavelength of the peak against 1 over the number of carbon atoms. In other words, to plot the energy gap against the reciprocal of the number of carbon atoms, because then you can extrapolate this line. You get a fairly straight line from which you can extrapolate the energy gap for the infinite polymer. And you can see it doesn't extrapolate to zero gap. You have quite a significant gap for the infinite polyacetylene, and that's because of this bond length alternation. But it is possible to make a molecule that doesn't have bond length alternation, and these are known as cyanines. So in these molecules which have nitrogen at each end, one of nitrogen with a lone pair and one with a positive charge. Now, if you plot the energies of a series of cyanine dyes, they form a line which appears to extrapolate towards essentially a zero gap. And that's because you have no bond length alternation, because you have a resonance. See, these are two resonance structures which contribute equally, where you have the lone pair, you can see, donating through to the positive charge. So the positive charge is equally delocalized between both ends. And you have this sort of completely equal bond length along the chain, no bond length alternation, which makes it behave like a free electron gas model. And so if this carried on to an infinitely long chain, you'd expect a zero gap. But I think you'll see that there's something a bit paradoxical here, because if it was an infinitely long chain, then the end groups wouldn't make any difference. And then it would be essentially the same as the polyene. So the two things must converge where they're infinitely long. And so what must happen is that actually, for a certain length, this does undergo a Piles distortion and must rejoin the curve for the polyene. So if we go back and think about how this works with single molecule conductance, I thought I'd show you some results for some real molecules. So this is a series of oligomers from another group where we've got sulfur atoms at the end. So the sulfur binds strongly to the gold. And we're just changing the length of the molecule and measuring the conductance as a function of length. So the results are shown here. If you plot the log of the conductance against the molecular length, you get a beautiful straight line corresponding to an attenuation factor of about -3 reciprocal nanometers. So that means the conduction falls steeply with the increasing length. I mean, this is a log scale, so the conductance is decreasing by a factor of 10. Each time you increase like one more repeat unit in the chain, the molecular wire becomes 10 times less conducting. And you can see that's a problem. If we want to make molecules for doing long-range charge transport, you're not going to be able to go very far if you have that large an attenuation factor. But if we look at the cyanine type molecules that I was just talking about. So these are basically the same as the cyanines that I was talking about earlier, except they've got sulfur end groups and benzenes to join up with the gold. And these are compounds that we have synthesized very recently in my lab. And now if you measure the conductance as the molecules get longer, you'll see, at least for the first 4 members of the series, there's almost no change in conductance with length. So that the conductance of the molecule is essentially independent of length, allowing us to get charge transport over longer and longer distances. Although for the longest one here, you do get a drop off in conductance, and I'll show you in a moment why that is. So if you look at the crystal structures, for the short ones, you get no bond length alternation. These are the crystal structures of the different increasingly long cyanine dyes. And for these 2 short ones, you have no bond length alternation. The histogram shows the bond lengths stay pretty much constant along the chain. But once you reach a certain length, then you do get this alternation in the bond length. And that's why the conductance starts falling with increasing length. So that's a little bit of work we've done recently on cyanines. All of the rest of this talk will focus on porphyrin derivatives. So porphyrins are what make blood red and grass green. They're naturally occurring important pigments, but they're also interesting molecules for making molecular wires because they're highly delocalized. And they're molecules that I started working with first during my PhD in Cambridge with Jeremy Sanders. And ever since then, I've enjoyed working with porphyrins, and about half my group, or probably more than half of the group, work with porphyrins at the moment. I thought I should show you how we synthesize these porphyrins because it helps you relate to where they come from. So they all come from pyrrole. Just condensing pyrrole with formaldehyde forms a dipyromethane, which you can then condense with a benzaldehyde to form a diaryl porphyrin. We normally insert zinc, but you can insert other metals. And then we brominate and do a palladium catalyzed Sonneger-Shearer coupling with an acetylene to put on these acetylenes, and we often join acetylenes together to make the molecular wires. These AR groups are aryls, and they control the solubility. And we use 3 main types. The ditybutyls are very good for growing crystals, but these longer, more flexible chains are more soluble. And the most soluble compounds that we work with a lot are these bis trihexyl silyls. So you need to have these groups to make the compounds soluble so that you can characterize them in solution and process them. Porphyrins, I think, have quite a bad reputation for being compounds that are insoluble, made in low yield, and only prepared in small quantities. So I'd like you to notice here that these are fairly decent yields. So, well, in each step, we're getting 70 and nearly 190% yield in the synthesis. And they're extremely soluble compounds that you can make on a large scale. And some of them are even liquids. So this monomer with the trihexyl silyl aryl groups, here's a batch which is 10 grams or 10 mil. And the pure compound is actually a liquid, which means that it's a really soluble compound, miscible with many solvents, and a good building block for making large molecules in a form which is soluble and processable. So we join the acetylenes together, often to make molecular wires. And here's an example of a dimer where we've just made a butadiene link between 2 porphyrins. And this is the crystal structure. You can see in the crystal, the 2 porphyrins are coplanar, and they happen to have coordinated pyridine. And these solubilizing aryl groups are twisted out of plane. They're not really part of the pi system. They're more controlling solubility than electronics. So smaller ligamers we can often characterize by single crystal X-ray analysis, but larger molecules are difficult to crystallize, and we often characterize by scanning tunneling microscopy. So these are images of a linear hexamer deposited on a gold surface by electrospray under vacuum and imaged by collaborators in Peter Beaton's group in Nottingham. So it's a linear porphyrin hexamer, and you can just see blobs for the individual porphyrin units. So you can't resolve the atoms, but you can resolve the porphyrins. And the distance between those blobs is just the same as it was between the zinc porphyrins in the dimer that I just showed you. And if you go to longer oligomers, they tend to become more flexible. So these are images of a polymer with about 40 zinc porphyrin units, again deposited by electrospray onto a gold surface. So now you can see these spaghetti-like chains, and you can just about resolve the blobs for the individual porphyrins as they stretch across the gold surface. So these are not just rod-like molecules, they're also electronically conjugated and wire-like. And you get some hint of that from the calculated molecular orbitals. So this is the HOMO, which has an anti-bonding interaction, and the LUMO, which has a bonding interaction at the center, which that lowers the HOMO-LUMO gap, and both of them extend over the whole dimer unit. And you can see that they are pi conjugated if you look at their absorption spectra. So this is the absorption spectrum of, this is the monomer, so N is 1, just in solution. And remember that the visible region is between 400 and 700 nanometers. So if I then compare the dimer, you can see that the dimer has already gone beyond 700, so its absorption is shifting into the infrared. And as we increase the number of porphyrin units up to 6, you get this very strong absorption band in the infrared. In other words, you get a reduction in the pi to pi star gap, showing that you've got strong conjugation. We can also look at the band structure of these sorts of infinite polymers, as shown here. So you can see that for the infinite polymer, you do expect a band gap, like in polyacetylene, so basically due to a Piles distortion. But if you change the way the porphyrins are connected, so if you make a tape where you have 3 links between every porphyrin, now the band has essentially 0 band gap, and so we predict these sorts of molecular wires to be semi-metallic. So having made these sorts of porphyrin-based molecular wires, we thought we'd test their conductance, and we did that in a collaboration with a group at Liverpool and Madrid. So they used the STM method to measure the conductance of molecular wires. So we made molecules with sulfur end groups and made a series of oligomers and tested their conductance. And the histograms are shown here. So for the monomer, the dimer, and the trimer, don't be distracted by this blob at the bottom. That's just due to noise, so I'll shade that out. But this plateau shows the conductance of the monomer, the dimer, and the trimer becoming progressively less conductive. You can see they're going down in the conductance scale. And also the breakoff point is getting longer, as you'd expect, because the molecule is getting longer. So if you plot the log of the conductance against the length, you get a nice straight line, and that tells you that the attenuation factor beta is again about 3 reciprocal nanometers, just like it was for the previous benzene-containing molecule. So the conductance does fall off quite steeply with length in these molecules. But if we test a different sort of molecule where we now have edge-fused porphyrins, now looking at the histograms and again hiding the noise, we can see that now the conductance of these molecules is essentially the same for the monomer, the dimer, and the trimer. All have essentially the same plateau conductance levels, and now the conductance hardly falls off with length, which is what you want if you want to mediate charge transport over long distances. So these are molecular wires, which are the simplest electronic components. We've also been investigating molecular transistors. So a transistor has to have 3 connections, 3 electrical connections, a source, a drain, and a gate. And it's essentially impossible to connect 3 metal wires to a molecule. There's just not space to get 3 contacts into a molecule. But you can make a molecular transistor by having the gate a little bit far away. So if you have a molecule between a source and a drain, and then you have a dielectric insulator and then a gate. So the gate's not directly contacting the molecule, but the electric field from the gate moves the energy levels up and down so they come in and out of resonance with the source and the drain, and that can control the conductance. So you can control the current flowing through the molecule by changing the gate potential, just like you would in a normal transistor. And we make these devices using a silicon substrate. So the gate is made of silicon with silicon dioxide insulator, and then graphene for the source and the drain. So we fabricate by electron beam lithography these hourglass-shaped bits of graphene with a very narrow constriction, and then apply a current, well, apply a voltage and measure the current flowing between the 2 parts, until we can just burn a little gap about 2 nanometers wide in the center of this constriction, and then deposit the molecule across that gap. And this is not a very reliable process. So we have to make these chips which have 874 of these nano gaps, and we deposit molecules across the whole lot and then automatically measure them. And if you're lucky, a few of them actually have a molecule across the gap, and then you can measure its behavior as a molecular transistor. And when you do that, you can measure the current as a function of the bias voltage, that's the source drain voltage, and also the gate voltage. So you get these sort of two-dimensional diagrams where the contour here is plotting the conductance or the current. And in these sorts of plots, you have different regions of the diagram corresponding to different oxidation states. So as you change the gate voltage, you can change from having a neutral molecule, the anion or the dianion or the cation or the dication. And you can get a lot of information also on the vibrational levels. Just like when you do a fluorescence spectrum or an absorption spectrum, you get vibrational fine structure. You see vibrational structure in these stability diagrams as well. And we're studying these at the moment, but I'm not going to talk about them more now. I'm going to move on to a different sort of molecule that we'll be looking at. Rather than linear molecular wires, cyclic molecular wires. And I'm really excited about ring-like molecules as molecular wires, partly because in everyday life, a straight bit of metal wire has fairly dull properties compared to a solenoid or a circuit. So I think it's interesting to look at molecular wires that are in rings or helices or other sorts of shapes. So we've been making these porphyrin-based nanorings, and we do it using a template. So the template fits perfectly inside the cavity of the nanoring, and we use the template to direct the synthesis. So in this case, the template with 6 nitrogen atoms binds to a zinc porphyrin monomer to hold the monomers in place while they're joined together, making these butadiene links by palladium catalyzed oxidative coupling. So that forms this complete ring. And the crystal structure of the product shows that you have a smooth barrel-shaped pi system around the template. And the template is not really part of the pi system. It's not conjugated or electronically coupled to the porphyrins. And you can easily remove it by treatment with acid or by using a high concentration of an amine. So we can use different templates to make different sized rings. But we can even use the same template to make different sized rings if we use different oligomer building blocks. So I'll show you how that works. So imagine what would happen if you had the same 6-legged template, but now your building block, rather than being a monomer, is a covalent tetramer. So the only monomer you've got has got 4 porphyrins already connected together. So all the products must be a multiple of 4 if you oligomerize those tetramers. But the template will tend to close any oligomer which is a multiple of 6. So the product is the lowest common multiple of 4 and 6, which is 12. So you get this 12 porphyrin ring formed in a figure of 8 shape very selectively and in decent yield. So nearly 40% isolated yield. And the crystal structure just proves that you have that figure of 8 shape with 2 bound templates. And we can characterize it by all the normal techniques like NMR and mass spectrometry, but we can also image it by STM on a gold surface after removing the template. So these are pictures of those 12 porphyrin nanorings lined up along a step edge on a gold surface. So you can count 12 porphyrin units around that ring. Each ring is about 5 nanometers across. So I showed how you can use a mismatch between the number of binding sites on the template, 6 binding sites in that case, and the number of binding sites on the building block, 4, to direct the formation of a larger structure with the lowest common multiple of binding sites. We call this principle Vernier templating, and we've used it to make many large rings. So here are some images of 10, 20, 30, 40, and 50 porphyrin rings that we've made by this way. And in all cases, you can actually count the porphyrin units around the ring. So you can make these really large molecules directly from small building blocks using this sort of template-directed synthesis, right up to the 50 porphyrin ring, which is about 20 nanometers across. So that's bigger than I talked about the minimum length of a transistor getting down to about 10 nanometers. This is more than twice that gate length of a transistor. And so we're excited about the idea of looking at charge transport around these large rings. It's quite easy to oxidize one of these porphyrin nanorings. So you can remove an electron and introduce a positive charge. And then you can wonder, does that positive charge just stay where it is on the porphyrin where it's formed, or does it move around incoherently between different sites, or is it delocalized as a wave function coherently over all 6 porphyrin units? And we've looked at quite a lot of different techniques to probe that question. But one way of studying this, which I want to talk about, uses aromaticity. So I thought I should remind you about Huckel's rule and the principle of aromaticity. So Huckel's rule states that if you have a pi-conjugated macrocycle with alternating double and single bonds, where you have 4n plus 2 pi-electrons, then the molecule will be aromatic, which means that if it's placed in an external magnetic field, you induce a ring current around the molecule, which induces a magnetic field inside the molecule that opposes the external field inside the ring. And you can tell that that's happening from the proton NMR spectrum, because if you look at this compound, you find that the external protons come at 9 ppm, whereas the internal protons are strongly shielded at -3 ppm. So that's evidence for an aromatic ring current, shielding the internal and de-shielding the external protons. You can also explore this computationally, and that the parameter that people normally calculate is called the nucleus-independent chemical shift, or NICS value. And it just shows the shielding or de-shielding due to the ring current. So this is a plot across the plane of the molecule showing how you have shielding on the inside and de-shielding on the outside because it's got an aromatic ring current. So that's what happens if you have 4n plus 2 pi-electrons. If you have 4n, you get the opposite behavior, it's antiaromatic. So for example, if you take this 18-aniline molecule and you reduce it twice to make the dianion, now rather than having 18 pi-electrons, it has 20 pi-electrons, and the ring current goes in the opposite direction. So it reinforces the external field inside the ring. And that means that the proton, which used to resonate at -3, now comes at almost +30 ppm, and the one that was at -9 comes at -1. And you can also see this from the calculated NICS plot. It's now shielded on the outside and de-shielded on the inside. And you can apply the same principle to porphyrins. So a typical porphyrin monomer is aromatic. You can draw a pathway of 18 pi-electrons with alternating double and single bonds. But if you oxidize it to the dication, it becomes a 16 pi-electron 4n system, and it becomes anti-aromatic. And you can see that from the NMR spectrum. So you can make those predictions just by counting single and double bonds through a pathway like this, and counting the number of electrons and saying, is it 4n or 4n plus 2? And you can do the same on a porphyrin nanoring. So if you count single and triple, you get the same number of electrons from a triple or double. Single or triple or single or double bonds all the way around this pathway. You conclude that the 6 porphyrin nanoring has 84 pi-electrons, so perhaps it should be anti-aromatic or non-aromatic. Whereas if you oxidize it to the hexacation, it now should be 78 pi-electrons, and it should be aromatic. And this very simple prediction from Huckel's rule turns out to be correct and is supported by high-level calculations. So these are the NICS calculations showing, so the color here reflects the NICS value. And it shows that for the neutral ring, actually for the neutral ring, it is non-aromatic. You get the shielding on the inside and the outside is the same. But for the 4+, it's anti-aromatic. So you get shielding outside and de-shielding inside. Whereas for the 6+, you get shielding inside and de-shielding outside. But that's just a computational result. I should show you some experimental evidence that shows you really do get these huge ring currents. So these are the NMR spectra in solution for a 6 porphyrin nanoring with a hexadentate template. So I've just shown a 6th of it there. And to start off with, this is a neutral molecule. So the neutral molecule doesn't have any global aromatic ring current, but each individual porphyrin is aromatic. And you can see that because the alpha, beta, gamma, delta protons are strongly shielded. So if you're an organic chemist, you'll know that pyridine normally resonates at about between 8 and 9 ppm, but here it's near 2. This alpha proton is near 2 because it's strongly shielded by the local ring current of the zinc porphyrin. But there's no global ring current, and you can tell that because these ortho and ortho prime, O and O prime, are almost coincident, and the trihexyl silyl signals are also almost coincident. But if you oxidize it to the hexacation, you can now see a wide splitting between the trihexyl silyl peaks, and the one which comes at highest chemical shift is the one on the inside. So that means you have an antiaromatic ring current. And you can also see that from the template protons. These alpha and beta protons are now at past 20 ppm, so they're strongly de-shielded by an antiaromatic ring current. If you carry on the oxidation to the 6+, you now get a ring current in the opposite direction. And you can tell that because the trihexyl silyl signals swap their arrangement. So the more shielded one is now inside the ring, and you also get a wide splitting between the ortho and the ortho prime. So that means we have an aromatic ring current, which is what you'd expect from the number of π-electrons. If you carry on oxidizing to the 12+, you can also record an NMR spectrum of that. And now you have no global ring current. And you can tell that because the trihexyl silyl signals are coincident, the ortho protons are almost coincident, but every individual porphyrin is now in its 2+ oxidation state. It has 16 π-electrons, it's antiaromatic, and so it's antiaromatic with the alpha proton coming right up at almost 12 ppm. So just by changing the number of electrons in the porphyrin, we can establish an antiaromatic and antiaromatic ring currents around the entire nanoring. So we've looked at lots of different rings like this to see if we can study global ring currents. And the largest ring that we've looked at so far is this 12 porphyrin ring. And we studied this with these large 6-legged templates, 2 of them in place, to hold the molecule into a regular circular geometry. And the calculated structure is shown here. And we have good evidence that it really does adopt this sort of structure in solution. So we made this compound and we studied its NMR in different oxidation states to try to see whether we have a global ring current around the entire perimeter. But the spectra were just too broad and we couldn't really assign them. So we synthesized a new template, which has these trifluoromethyl groups here. And that means that you can probe the shielding or de-shielding inside the ring from the trifluoromethyl resonance. And since there's only one type of fluorine in the whole molecule, it doesn't matter if the fluorine NMR signal is broad, you can still know where it is. So if you look at the NMR spectra, both proton NMR and fluorine NMR of this 12 porphyrin nanoring bound to those templates in the 6+, 8+, 10+, and 12+ oxidation states, you can see that there's a shielding in the fluorine peak in the 6+, meaning that it's aromatic, as you'd expect for 162 π-electrons. And in the 8+, it has an anti-aromatic ring current, 10+ a slightly aromatic one, and in 12+, it's essentially non-aromatic. So you get that most clearly by looking at the fluorine NMR, but you can also deduce it from the trihexyl silyl peak, although it's quite difficult to assign the inside and the outside trihexyl silyls. I thought I'd show you the crude NMR spectra from this titration. So we do an oxidation titration where we start off with a sample of the neutral ring and we add an oxidant. We add this radical cation oxidant to gradually oxidize the molecules. So the number here is the number of equivalents of oxidant. And we look at how the NMR spectrum, the proton NMR and the fluorine NMR evolve. And the first thing you see is these sharp peaks at about 7 ppm. And they're from the reduced oxidant. So as you add this oxidant, you get just a neutral compound formed. And that's quite useful because it lets you check how much you've added. And when you reach 12 equivalents of oxidants, that means every porphyrin is oxidized once, then you start getting free oxidant and it exchanges and it broadens out this signal. So you have a good check that you've got to a stoichiometry of 12 equivalents of oxidant at that point. And then now if you look more carefully, you can see different signals arising, particularly in the fluorine NMR. As you add the oxidant, you see the 6+ being formed, and then that goes away and you get the 7+ and the 8+ and the 10+, and the 12+. So you can measure the ring current and the shielding effect in all these different oxidation states. One of the interesting things about this 12 porphyrin ring is that we can change its shape using templates. So we can lock it in either a ring type shape or a figure of 8 shape. And I was particularly interested in this because if you think about a loop of metal wire in a figure of 8 shape, you don't expect to induce any ring current if you place it in a magnetic field, because the amount of field going through one side is equal to the amount of field going through the other side, and they have the opposite effect on they induce an opposite ring current, so they should cancel out. So we decided to compare these two molecules, which they have exactly the same perimeter. Their complex is the same 12 porphyrin ring, and they both have two 6-legged templates inside with fluorine probes. It's just one of them has two very large 6-legged templates, so it has a circular shape, where the other one has two small 6-legged templates, so it has a figure of 8 shape. So we can look at the NMR of both of them while we oxidize them. And when you do that, well, I've already shown you the results for the circular one, but when you do the same thing for figure of 8, you see absolutely no ring current. So I think we can be certain here that the 3-dimensional conformation has prevented the induction of any ring current. So it's nice to see that simple macroscopic idea does translate into the molecular world. So these are by far the largest aromatic molecules that anyone's looked at. If you look in a more or less any textbook of organic chemistry, it will tell you that aromaticity and Huckel's 4n+2 rule stops at about 22 pi-electrons. So it's interesting that here we're seeing it not just at 22, but 162 pi-electrons. We're getting evidence for an aromatic ring current. And one reason why I'm interested in these large aromatic rings is that you get similar sort of behavior to aromaticity in non-molecular rings. So if you have a ring of aluminium metal, and you place it in a magnetic field at low temperature, you get a ring current which carries on indefinitely. So it's not dissipated. Even though the ring has some resistance, the current is not dissipated. It's a quantum mechanical feature of the ring. So it's very much like an aromatic ring current. But one of the differences between this ring current in a metal ring and a molecular ring is that the ring current in the non-molecular structure changes as a function of the applied magnetic field. So this is a plot of magnetic field against ring current. You can see it grows and then it decays and then it goes in the opposite direction and it cycles as a function of the applied magnetic field. And no one's seen anything like this in molecules. And I think the reason that it hasn't been seen in molecules is the amount of magnetic field required for one of these cycles is inversely proportional to the cross-sectional area of the ring. So it's proportional to 1/πr². So the largest magnetic fields that you can easily get in the laboratory are about 20 Tesla. And in order to see one of these cycles for 20 Tesla, you'd need a molecule which is about 20 nanometers across. And no one's looked at an aromatic molecule anything like that big. But I hope that in the future we might be able to and we might be able to make a connection between these mesoscopic physics effects in microfabricated rings and ring currents in molecules. Another reason why it's interesting is that if you can see a ring current in a molecule, it means that you have a coherent wave function transporting the charge around the entire system. And that means that if you have a ring-like molecule connected between two electrodes, if you have a coherent wave passing by two pathways, then if they're exactly in phase, you get constructive interference. But if there's a slight difference between the two pathways, or if you can introduce a phase shift with an electric field or magnetic field, then you'll get destructive interference. So you might get an interferometer where you can measure very slight shifts in phase between the two pathways, measuring weak magnetic or electric fields. It might be a sensitive sort of transistor. So we're interested in putting these large aromatic rings into single molecule electronic circuits. So I think that's all the results that I'm going to tell you about today. I hope that I've shown you that we can make some unusual molecular nanostructures. I'm sorry I haven't talked at all about optical properties, but I think they have interesting electronic properties. They do also have interesting optical properties, but I just didn't have time to cover it today. I need to thank the people who've worked with us on this project. We don't actually have a scanning tunneling microscope in my lab. We do all that work through collaboration, mostly with Richard Nichols' group in Liverpool and Nicholas Agreit's group in Madrid. So we have many collaborations for single molecule charge transport. And also there are many people in my group who've been involved in the synthesis of the linear and the cyclic wires and looking at their properties. And the imaging I showed was done in collaboration with Peter Beaton in Nottingham. And we're studying with physicists like Laura Hertz in Oxford. Thank you very much. So there's time for questions if there's anything you'd like to ask me about that. Shall I stop sharing my screen?
Professor Anderson, thank you for an amazing talk. And now it's time for the Q&A session. So if you have any questions, either type them in the chat or join the call. Maybe before someone joins, I have a question. How do you actually synthesize those like porphyrin rings? Because I mean, how do you control that they are the size you want them?
From the templates. So, I mean, I showed you that how we can use a single template to build a ring that matches the template, or two templates in that sort of the Vernier principle where we built it from tetramers. So we use the templates to control the synthesis and to make specific sizes. I mean, for the larger rings, we often get mixtures of sizes. The synthesis is not perfect. So we use chromatography methods to purify particular ring sizes.
Okay, great, thank you. And now, like there is a question from this person in the YouTube chat, so I can read it aloud. Unfortunately, I missed the first part. What is the dimensions of a nanowire you can achieve?
Well, the dimensions of the nano rings that we've made are up to about 20 nanometers. And I guess the length is probably about, yeah, the trouble is if you make a really long one, it's flexible. So you don't know how long it is in a particular case, but we normally make structures that are between 2 and 20 nanometers across.
Great, thank you. Are there any more questions from? Because it looks like there is nothing more in the YouTube chat.
Okay.
So, Professor Anderson, many thanks for the great talk and for answering the questions.
Okay.
And as I already mentioned at the beginning, there will be no more regular talks this term, but definitely join us for the pub quiz and social event this Sunday and for the TCS symposium next Sunday. And thank you for attending the talk and have a nice evening.
Thanks. Thanks for hosting me. Bye.
Thank you.